Today we are going to have the lecture 6 of data structures and algorithms. So the lecture 5 video would be shared. I mean, video has been uploaded, but it will be shared on LMS today, and then lecture 6 would be uploaded, right? So in last 2 weeks, so basically in last 2 weeks, so we talked about these computational complexity analysis. Okay, so so there are 3 methods that we are using, mainly. Experimental studies, and then counting primitive operations, and then asymptotic analysis. In asymptotic analysis, so we consider, so mainly, so we have a way of comparing worst case and best case, in some cases both of them, right? Worst case time and best case time, and then based on that we decide the complexity of an algorithm, right? So there are 3 ways. Big O notation, 3 notations are used in asymptotic analysis: Big O notation, omega notation, and theta notation. Right? In Big O notation, we define the upper bounds of an algorithm. In mathematically, we get the upper bound of a function, right? So in when it comes to our algorithm analysis, so algorithm is like we check how algorithm is algorithm's time, right, is changing with the input size, how it is changing as a function, and then that function we find the GA, or the upper bound of that function. A function එක යන්න පුළුවන් නරකම තැන යන්න පුළුවන් උපරිම time එක. ඒක තමයි අපි big O notation එකදී ගන්නෙ. So we find the upper bound. And the theta notation we get, omega notation we get the lower bound, the best case, right? And then in theta notation we get both upper bound and lower bound. So this is the definition of Big O notation. So Big O notation, we define a function GA for a given fn function with the help of 2 constants, C and n0, right? For all n which is greater than or equal to n0, so we define a Gn which satisfies this equation. So Fn is always less than or equal to CGN. Right. Fn එක හැම වෙලාවෙම CGN වලට වඩා යටින් තියෙනවා. එතකොට GN වලින් අපි define කරනවා upper bound එක මෙන්න මේ Fn function. So then if this can be satisfied, right? So then we call Fn is big O Gn. So that means, so we say just Fn is a type of Gn. Gn වර්ගයේ එකක්. Fn කියන function එක අපේ function එක, our function is Gn type function. So something like that, right? So here is the graphical explanation of that. So we have CGN. CGN is always greater than Fn if n is greater than n0. n0 වලට වැඩි සීමාවෙදී n0 වලින් එහා සීමාවෙදී තමයි වෙන්නේ මේක CGN එකට වඩා වැඩි වෙන්නේ. So what about n is less than n0? What about this area? So that area we don't care. It could be greater than Fn could be greater than CGN or less than CGN. No, it could be the same. We don't care. We only consider, so the meaning of n0 means that's where we start to check. So it is like, right. So now we are in our lecture series. So now we are in the 4th week. This is sixth lecture, right? Right. So if I have the first lecture, second lecture, third lecture, and like 6th lecture. So I am going to consider the attendance. I'm going to monitor the attendance closely from this week. So before that, if you haven't attended my class as well, I don't care. So I only consider like this area, I don't care. I'm going to check that from 6th lecture, from this lecture, right? So likewise, so we are going to consider from n0, right? Before that, we don't care. It doesn't matter, right? Whatever happens, right? n0 වලට වඩා වැඩි වෙලාවෙදී මෙන්න මෙහෙම වෙනවා නම් එතකොට අපිට කියන්න පුළුවන් CGN Fn වල upper bound නියෝජිතය. So the upper bound representation of Fn is Gn. C can be just ignored and we can just say Cn. Sorry, Gn. Okay. So that is the big O notation. That's the definition. It is not very difficult. I mean, the idea is very simple. So so when we consider Gn or the big O of any function, Fn function, if you find a big O function of that Fn, so that big O function Gn doesn't have to be always in upper. So that's the idea here, right? Right. Gn doesn't have to be upwards, right? Like in it doesn't have to be upper bound always, right? Can hammer value එකකටම මේ Gn වැඩි වෙලා තියෙන්න ඕනේ නැහැ. It doesn't have to be some way up, like above the Fn. It doesn't have to be above the Fn always. So Gn could be sometimes lower than Fn. It could be, right? But the area that we consider, if we can define a value like this, so then this area, the area of our consideration, the CGN has to be above the Fn, right? Above the Fn. So likewise in my lectures, from this week on, like including this week, from this week, so I'm going to monitor the attendance. So your attendance should be good from this week. Right, that's the idea. Okay, right. So properties of a big O notation, we discussed that. Characterize the growth rate. So the function is characterized, right? So if someone asks, so how is your algorithm, right? So we can give this big O notation, big O value, and we can say, okay, so my algorithm is like this, right? So for example, if someone asks how is for example, like so there are a lot of my friends who are working in software companies, right? So most of my university friends, almost all are working in software companies. So now they are in for example, architecture level and then manager level. So sometimes they ask, how are your students, right? So then, so if I can provide an example student, which is who is a representation of all my students, right? So then I can show, so my students are like this. So this is one student, one example. So this is how my students are, right? So then they can have an idea, okay, right? So this student can do this and do that, and then his GPA is like this. He can do this kind of, he's capable of doing this. He's having these technical skills, and likewise, so they can have an idea, right? So if they ask, කොයි වගේ ළමයිද ඉන්නේ ඔය කට්ටියගේ මේ ෆැකල්ටි එක කොයි වගේ ඩිපාර්ට්මන්ට් එක කොයි වගේ ළමයිද ඉන්නේ කියලා ඇහුවොත් එහෙම මම ඉතින් මට පුළුවන් නම් දෙන්න එක්සැම්පලරි ස්ටුඩන්ට් කෙනෙක්ගේ CV එකක්. මෙන්න මේ CV එක පොඩ්ඩක් බලන්න, මෙන්න මේ වගේ කට්ටිය තමයි ඉන්නේ. So then he can have an idea. So big O notation is something like this. It characterizes a function as closely as possible. Right? So for example, like even for our department, now we are creating that. So we have something called graduate profile. Graduate profile. Graduate profile. So we define how one of our student should be. So a student who is graduating from our department, what are the things that he should have, or he or she should have? So the big O notation is something like this, graduate profile. So now we are in the process of creating graduate profile. And actually we had graduate profile for our faculty, but now we are just updating it, and we are going to create a more precise and more comprehensive graduate profile, right? So big O notation is something like that for algorithms. So if we have an algorithm, so we are going to characterize that algorithm using big O notation. If someone asks how is your algorithm, how it is behaving, so then we can provide a value. Okay, so my algorithm is behaving like this. So if I have an algorithm, so if I say, okay, so my algorithm is big O n. So then he would say, oh, okay, very good, very good. Right. So then another person, so he asks, how is your algorithm? So then he would say, okay, my algorithm is big O n squared. Then he would say, okay, so then it's not very good. Can you improve that? Right. So likewise, like by looking at this value, anyone can have an idea. We can have an idea on the algorithm. Right. So that's the thing. They characterize function or so you can replace this with an algorithm as closely as possible. So we should strive, instead of describing function in the big O, in simplest terms. So, okay. So we are going to use the simplest terms, right? Okay. So we talked about several functions, right? So in big O notations, we use different functions, right? So this is where we stopped last week. And today we are going to continue from there to discuss each of these functions. So I asked you to study these things. I don't know whether you have done that, but I'm going to ask some questions based on these functions, right? Okay, right. So let's take one student, right? Chalana, right? Chalana. 810 Chalana. Can you hear me, Chalana?
Yes, sir.
In the last week notes, so I have given constant function. Constant function. So what is constant function? Constant function එක කියලා කියන්නේ මොකද්ද? මේ මෙතන දැන් මේ මම ඇඳලා තියෙනවා. Constant function එක මොකද්ද?
That value in output are all are same.
Exactly. Yes. Good. So even the x value is changing, y value is a constant. That's the thing, right? Very good. Right. When it comes to okay, thank you, Chalna. When it comes to our algorithms, so when the input size, so input size usually we use n input size, If it is an array, so that's the array size. If it is a string, the string size, so whatever, the input size. When input size is changing, the time that it takes in our algorithm, it is not changing. Input size is changing, but the time is a constant. So the කොච්චර array එකේ size එක වැඩි කොච්චර වැඩි වුණත් දැන් අපි මේ කතා කරන දෙයට so යන්නේ constant time. හැම වෙලාවෙම අපි හිතමු නිකන් milliseconds 10යි කියලා. So always it is 10 milliseconds, for example. Right? So for example, if we take an array, right? Suppose so this is the size is 8, right? The array name is suppose it is A array name, right? So then if I want to access any value using index, right? For example, 10. And then I assign a value. Suppose this is an integer, right? To do this, right? To do this activity, suppose it takes 1 millisecond, right? මේකට 1 millisecond වලට වඩා මේ මම කියන්නේ නොගෙනිය හැකි තරම් කාලයක් යමකට යන්නේ, right? Suppose, right, just think it takes 1 millisecond for this, right? So then think that array size is 10. It takes 1 millisecond. If array size is 100, still it takes almost the same time. If array size is 1000, or 10,000, no, 100,000, 1 million, the time would be the same. Because this activity does not depend on the array size. කියන්නේ array එකේ index එක කියන්නේ මේ 10 වෙනි index එකේ තියෙන value එක access කරන. Accessing array value with its index. That activity does not depend on the array size, right? So in array, usually like if we take pointer perspective, right? So with array name, we keep the address of the first array item, right? So we have the address of the first array item. What we do here is we just add 10 into this address, and then we can directly access the address of the 10th item. It is just one calculation. The time it takes for that calculation is the time it takes for this, to that calculation, as well as to assign the value, right? So it is a constant. It does not depend on the array size. So in our algorithm, suppose we have several activities which are all similar to this one. they all they does not do not depend on the array size. So it's always a constant time, right? So it will add up other set of activities. So altogether it will be just suppose it is 25 milliseconds altogether for the program to execute. The runtime would be 25 milliseconds always. Does not matter the array size is the size of the array. So basically, with the size of the input, the execution time is always a constant. This is called constant time complexity. Constant time complexity. Right? So we give that as this constant time complexity. Big O1. This is the constant time complexity. Right. The second one, logarithmic function. Logarithm function. Log function, basically log function. So if when log en, so b is the base, right? B is the base. Log 2n, log 10n, right? So likewise, so we can provide log value. So usually log function goes like this. So it is having, right, at the beginning, the changing is rapid changing, but with the time, so it is becoming right. The beginning, it is rapid changing, right? But with the time, it is changing like this. මුල්ටිකේදී මේ වෙනස් වෙනවා ඉක්මනට වෙනස් වෙනවා වැඩි වෙනවා. හැබැයි ටයිම් එක යන්න ඒ වෙනස් වෙන ශීඝ්‍රතාවය අඩු වෙනවා. It is like here it is getting closer to the constant. Constant එකට ලං වෙනවා එන්නේ. Constant is something like this. Constant එකට ලං වෙනවා. This is log. Beginning it is changing rapidly, but with the time, it changes to some smaller changes. This is logarithm or log function. This is again n, and in our case this is t. So if we take one example, so I'm going to explain this example later, but for example, binary search. Binary search is having this kind of variation. When the so in a binary search in an array or similar data structure, in binary search, if the size of the array is increasing, so however the time is not increasing as n has increased, right? And then n වැඩි වුණාට සමානව, right? time එක a සමානව නෙවෙයි වැඩි වෙන්නේ, right? So for example, if n is so I don't know, like let's take just random values, right? 10, right? It's so wait for a moment. It is very noisy. Sorry. So there's a June Pang and a helicopter. Speed wise, both are the same. Right? You cannot catch a helicopter similarly. So it's same for the June Pang. You cannot catch that. Right? Okay. Right, okay, both are gone now. So n is changing, right? Suppose this is 10, this is 20, this is 30, right? But the times are not changing like that, right? So the time, for example, 5 milliseconds. So then this one for the 20, it is like 7. And then 30, it would be like something like 8. So there are 2 here, and it is just 1 here. Like likewise, it is different, right? Compared to these variations. So binary search is one example of this. So I will explain why binary search is log n. So in that case, so we call binary search is having big O log n. Right? Big O log n. So this is how we express that. Right? Logarithmic function. Right? The beginning rapidly changing, but then with the time that changing is mild, right? Not so rapid. Right. So the next one is linear function. Linear, right? So don't get confused with the linear right? Yeah. So the idea here is it is like a line. It's just a linear. It is a straight line, straight line. When n is changing, the t is changing in the same right. So this is suppose this is 10, this is 30. Right. This is this is 20 and then 30. So this could be 2. This could be this could be 5. This could be 7. This could be 9. So likewise, this could be 2. This could be 4. This could be 6. Likewise. 10 නම් 20ට යද්දි දෙකකින් වැඩි වෙන්නේ 20 නම් 30ට යද්දි ආපහු දෙකකින් වැඩි වෙනවා. Right? It is linear time calculation. So it is like big O n. So this is how we give the value. So I will give examples. So linear time. So the function is so we can give fn equals n. So fn equals n. That is given an input value n, the linear function f assigns a value n itself. Right? It is something like this. But actually, like so fn equals n. The idea here is actually it has to be the same, right? Like y සමානයි x. අනේ ඒ වගේ ෆන්ක්ෂන් එකක් නේ. ඒතර ඇත්තටම මෙතන මේ values ටික එන්න ඕනේ මේක 10 නම් මේක 10 මේක 20 නම් මේක 20 මේක 30 නම්. So when it is 30 it has to be 30. But actually, right? So in so if we take other linear function, they don't go from like they don't cross 0. So however, this is also linear. So this is also linear. And another function. Right? Again, it is linear. We consider both as linear. ඒක අර බිඳු හරහා ගියේ නැති වුණා ඒවල linear කියලා තමයි අපි සලකන්නේ. So big O n. ඒ කියන්නේ දැන් මේ size එක 10 දී තප්පර 10ක්ම වෙන්න ඕනේ නැහැ. ඒ තප්පර ගාන වෙනස් වෙන්න පුළුවන්. හැබැයි ඒ වෙනස් වෙන ශීඝ්‍රතාවය සමානයි. This is called linear, big O n. Don't get mixed up with constant and linear, right? Constant, linear, two things. Constant means it is always one value. Big O 1. This is linear. This is big O n. This is constant. This is linear. අටලගන්න එපා. Constant big O 1, linear big O n. Right? So then n log n, the next one. Basically, it is a combination of, so we have linear function. Linear is n, right? Big O n. And then we have log function, big O log n. It is a combination of linear and log. Right, so we have n, so we have log n. Multiply this, we get n log n. So that means in our algorithm, so we have linear part as well as, so we have logarithmic part. Again, අපේ algorithm එකේ එක කොටසක් තියෙනවා linear යන, අනිත් කොටස logarithmic විදිහට. So ඒ දෙක එකතු වෙලා එන time එක තමයි n log n. N log n. Fn equal n log n. That is the function that assigned to an input n the value of n times the logarithmic base 2 of n. This function grows a little more rapidly than linear function and lot less rapidly than the quadratic function. So n log n, so here I have given x log x, x multiplied by log x. This is how it advances with the x. Right. This is how it advances. So usually it is considered as between so we have constant and then we have logarithmic and then the linear and then the next one goes something like this, n log n. So this is n, this is log n. This is one constant. The next one would be n squared. N squared. It is called quadratic, so I will explain. So n log n is in between n and n squared, linear and quadratic. It is in between. N log n. So for example, so if I put some examples, like for this one, I have given example. Log n, I gave like binary search. Binary search. I will explain why binary search is log n. So then n, linear search. Linear search. Linear search. So if the size of the array is 100, we compare 100 times. If the size is 1000, we compare 10,000 times. So likewise, it is linear in linear search. And then bubble sort. So bubble sort is n squared. Bubble sort. I will explain why bubble sort is n squared. Bubble sort. Then in next semester, we are going to learn sorting algorithms. For example, quick sort. Quick sort is n log n. So it is better than bubble sort. Right. So binary search is better than linear search because it is log n. Right. Okay. So n log n, combination of log and linear. N log n. So then quadratic function. Quadratic function. So another function that appears often in algorithm analysis is the quadratic function. So Fn equal n squared. N squared. Right. So that means so with the time, quadratic. So I missed a quadratic. Okay. Quadratic function. So usually if we take n and t, so it goes like something like this. Right? If n is 10, so we have a value. Right, so then if n is 20, so look at how it has changed, right? So then if we take the same, like same distance in here, 30, right? So then, so this value is way too higher than this. Suppose this is 2 seconds, right? So this one would be so way higher. Okay. So I can go to this example. So here, see the values. If n is 8, n squared is 64. So likewise. Suppose this is 100. Right. So if this is 100, so then it should be 400. This should be 900. Something like this. I know. So similarly, if it has a similar shape but does not cross the 0, so that's also fine. So we consider them as n squared in our case, right? So big O n squared. Quadratic function. The main reason that the quadratic function appears in analysis of algorithm is that there are many algorithms that have nested loops. So I'll explain that. In our programs, so if we have nested loops, if we have a for loop here, and then inside that another for loop, right? So this is very common structure. If you have 2 for loops like this, so I mean, there should be some conditions in these for loops. So those should be there to become a big O n squared. Like if we have such programs, so then the time complexity would be n squared, most probably n squared. Nested loops, if they're having nested loops. So bubble sort is having a nested loop, if you remember, right? So let's talk about that, right? The quadratic function can also arise in the context of nested loops where the first iteration of the loop uses 1 operation, the second uses 2 operations, the third uses 3 operations, and so on, right? So it could be just a simple nested loop, right? Like For example, F4 in I 0, I goes up to N I plus plus. So then we have for loop, and then nested, right? Int J goes up to N J plus plus. Again, it is right. So whatever the code, some other code could be there, but there should be 2 for loops, because this loop goes up to N. Remember, it is N. Huh? This is up to N. Again, the second. And incrementing 1 by 1. Right? So in this case, when the first loop iterates just one time, because when I is 0, right? J goes from J iterates N time. Right? For I, one value of I, J iterates N time. Then similarly, I iterates N time. Each time it is iterating N, right? So it is, so how many times? How many iterations? N multiplied by N. N squared. So that's why it is big O N squared. Suppose we are having an array size N, right? So this goes like this, and then in the inner loop, again, we go like this. So then size again with the time maker N squared value. So that's why we call it big O N squared. So this is the very straightforward quadratic big O quadratic algorithm. It's very clear, it's very straight, that we can see this goes N time, this goes N time. It is big O N squared. Right. So, however, some cases, so there are some cases, right? For example, for I equals 0, I goes up to N, I plus plus. Suppose the second, no, it's the same. So in the inner loop, I equals 0, I, okay, in this case, okay, I is less than or equal to sorry, this is J, no? J, right? J. J is less than or equal to I. J again. If you have this situation in your algorithm, so in this case, right? So no problem here, right? I is from 0 to n, right? N times, right? But here, J is from 0 to the value of I at each iteration. So that means in the first iteration, when I is 0, J goes from just 0 one time. When I is 1, 0 and 1, 2 times. 1 time, 2 times. How many times here, right? Times. Then I is 1, 2, 0, 1, 2. That means 3 times. Because 3 times it is running. Inner loop is 3 times. I is 3. Inner loop is running 4 times. So likewise, n with the n minus 1 with the n times. 10 times. So the number of iterations, if we add all these ones, right? So then it will be something like this: 1, 2, 3, 4, and so on to n. Yeah. So the program is running this times. So in our previous case, right, our straight, this one, n, I goes up to n and j goes up to n. In that case, so if I draw that, if I is 0, n times. If I is 1, n times. If I is 2, n times. So likewise, n plus n plus n plus n up to n times. මේ ටික ඔක්කොම එකතු කරාම තමයි අර n squared එක එන්නේ. Right? n ඒවා n වර්ග. n value is added n times. Right? But here we add like 1, 2, the first time it iterates 1 time. Second time it iterates 2 times. Likewise, it is added. Like this. See? So usually the value is n n plus 1 divided by 2. No? Yeah, 2. So this is the answer of this. Right. But if you check this value, right? If you analyze that, it would be something like n squared plus n divided by 2. Right? So then it is something like n squared divided by 2 plus n divided by 2. Something like this. And then further I can check like n, let's write like half n squared, right, plus half n, right, something like this. But even in this case, so this is the value, right? But still we ignore this one and this constant. Still we consider it as n squared or log big O n squared. Big O n squared. So this is the actual value. But from this actual value to represent this function, we choose n squared. Right? So we consider it as n squared type. මේ වගේ එකක් වුණත් අපි සලකනවා n squared type එක එකක් කියලා. මොකද ඒකේ n squared වර්ගයක් තියෙනවා. Actual number of actual time, actual number of iterations are less than n squared. N squared case. So this is actual n squared case. But the actual number of time it iterates is less than that, but still to represent this, we choose n squared. Is it clear? So when we are choosing our big O value, when we are choosing our big O value, we choose not the exact time or exact value, but an estimation. A closer value which can represent our function or our algorithm. ඒතර මේකේ තියෙන අර constants. ඒ කියන්නේ අපි මේකේ බලනවා, so we check. So here n squared, this is n, right? The most influence on the time would be having from n squared. So that's why we choose it is as our. So we just ignore this n part. So this part is ignored. And then the constants would be ignored. So remember again, big O value is not exact value or exact time it takes. It is a rough estimation, and then it is just a representation of our function or our algorithm. Is it clear? right? So quadratic function. In quadratic case, we consider it could be n squared or something like this, right? This type of things are also considered as n squared. So if we can find nested loops, yeah, we can consider it. So if you remember, if you go back to bubble sort, you will find similar pattern. The sorting algorithm that we discussed, right? They may have similar pattern. So we'll discuss later, right? So I'm going to give some examples. So this is quadratic function. See, so forget about this part. So this is the just the function, how it is drawn, right? But consider this part, this part. So in our algorithm comparison case, so we don't consider minus, right? So this area is the relevant area for us. Then cubic function. Cubic function is fn n cube or power 3. It assigns to an input value n product of n with itself 3 times. Right. N 3 times. Cubic. Now, you can understand, I think, suppose if we have 3 nested for loops. Suppose this one goes up to n, and this one goes up to n, and this one goes up to n. So in this case, you can identify, right? The number of iterations would be generally 3 n's with multiplications, n squared. Sorry, n cube. Right. So cubic function. So it is something like this. It is more rapid than quadratic. Cubic function. Then exponential function. So exponential function. So here n is here, right? So even in so n squared. So n is here, right? But now in exponential, n goes up here. Right? 2 to the power n. Right? It could be 2 or 3 or any base value here. 2 to the power 3 to the power n. 10 to the power n. Exponential. n goes up to. So B is a positive constant called base. So B is the base. It could be 2, 3 or whatever, the value, positive value. And the argument n is the exponent. So we call n is the exponent. So, so one example, right? So if we have a loop that starts by performing one operation and then doubles the number of operations performed with each iterations, then the number of operations performed with nth iteration is 2 to the power n. So if we have a loop, so we perform something and then the next loop, the first iteration we do something. In the next iteration, the number of times we iterate, like the things that we do would be double. And so on. So I'll give some examples like so there are many examples for this one. So most of these examples are like we are going to talk in later lectures. So I will explain there, right? So exponential function, right? It is way, way rapid than the previous cases. So this is the function. Okay, so any questions up to now? The things that we have discussed up to now. So exponential function, so exponential growth. So one example would be, so most of the recursive functions. So recursive functions are exponential. For example, like Tower of Hanoi. So that's one example. So I'll give it in the next set of slides, right? Okay. Right, okay. So check this program, right? If it is not clear. So this program. So in this program, so we have, so this method, right? So we are taking in an integer array. We are taking an integer array and then we get the length of that array as n. integer. And then okay, so we are going to find the maximum value of that array. We want to find the maximum value in that array. To find that, so we have a loop. Loop goes from 1 to n. Because the first value data, the array name, index 0 value is first we are taken as the maximum. 0 value එක මුලින්ම maximum එක විදියට දාගෙන, so we start with 1 and then we go up to n, right? So if the data, the item that we are checking is greater than the current maximum, the maximum value here. If it is greater than the current maximum is assigned with that new greater value, right? So this is a very simple program that we discussed in our first semester, right? So basically this program iterates n minus 2 times, ne? Yes. No, n minus 1 times. N minus 1 times. N minus 1 time. And then finally we return the current maximum. It is returned. Okay, so can anyone tell me what is the big O value of this method? So what is the big O value of this method? Anyone? Can you guess? Okay, so Vidushan, so most of you are saying that it is big O n or linear, right? So Vidushan, are you there? Yeah. So can you explain why it is big O n? Vidushan, why it is big O n? So you say you say it is big O n. Why is that? Yeah, so the array size is n Yeah, that's fine. So that's fine, Vidushan. So if you're wrong, so that's fine. So can you tell me why you just say it is n? Okay, so then who's next? Arafat. Arafat. So can you explain? Not just to me, but to all, Arafat. Arfat, are you there? So can you explain, can you tell others too your answer? Why it is n? Yeah, so our input n, the loops are, it's looping n times, so like approximately n times. Exactly, it is it goes from, so it goes from 1 to n. Actually, it stops when it is n0, 1, right? So basically, it iterates n minus 1 times, right? Suppose n is 1000, right? So this would be n minus 1 million, 9 right? So this is I mean, almost the same. So we just consider it as n, right? This program iterates n times. මේ program එක මේ loop එක මෙන්න මේ ටික execute වෙනවා. So this part executes n times, almost n minus 1 times. So I just consider it as n. So n times, n times this part is executed, right? So in that case, we can say it is big O n, linear. So this is linear. So however, the exact time it takes would be, so for example, so we have something here. So we have something here, assignment operation. And then we have another assignment operation. And then the length up. So it doesn't matter, right? Okay. So these assignment operations are there. And then we have return operation, right? So then, so we have another assignment operation, and then the comparison operation, right? And then this part, and then again increment, and then the assignment likewise. So we have some additional operations as well, right? So if it takes, for example, this takes x time, right? The first line it takes time x. The second line it takes time y, right? Then the other assignment there it takes time c, right? And then the there are iterations. So I'll take for instance A, B, C, like those are the times. Those are the times. Time A for the first line, time A for the second line, and time C for this assignment. And then these comparisons and this increment and this part, suppose it takes all together, it takes X, right? X, then how many times it iterates? X, and how many times it iterates? Almost n times, right? N times, and then for the last return part, it takes this n. This is n. Suppose it takes d. So the actual time would be something like this for the first line, second line, and so on, and then this. If we compare this with other times, right, the most of the times would be taken by this. So therefore, we can ignore others. So these constant parts would be ignored. And then this part can be ignored. So that's why we consider it as n. Right? So that's how it becomes big O n. To represent this, we use this. That's it. Okay. So if we have a loop, so then we have to closely look. Okay, so this is where it takes time, right? Suppose if you remove this loop from this program, then it will be constant time, right? If we remove this from that, then it will be all constant. So that's what it will become big O1. Okay. So this is big O n. Algorithm array max for computing the maximum element array of n numbers runs in big O n times. So in this case, definitely it will go up to n, definitely. So the worst case, the best case, there's nothing such, right? n කියන එක මොන value එක වුණත් හැම වෙලාවෙම මේක මේ loop එක n දක්වාම යනවා. අන්තිම value එක දක්වාම යනවා. So to find the maximum value, we have to check all the values. We have to check all the values. Right? Right, another example here. So in this example, we take a character, but we take char variable, and then we take n. We just take a variable and we take integer. and then we create string, right? At the beginning, it is an empty string. A string answer. Right? Then, so we have a loop. Loop goes from 0 to n. And then it iterates one at a time, right? So basically, if you're looking at this loop, so loop iterates from 0 to n, basically. 0 up to n, not including n, right? So then, so this answer, this variable, the string, so we append C. We append C one at a time, right? Right. So we have a string. First, it is empty string. So in the loop, first, suppose our C is, suppose it is character A, right? So then we append A, all right? And then in the next iteration, we append another A. And then in the next iteration, we append A. So likewise, we append A. එක පාරකට එක ගානේ එහෙම append කර කර යනවා. Right, so can anyone tell me what is the big O value of this method? You can guess, no problem. If you're wrong, if you're right, it is good. But if you're wrong, it's very, very good. Right, so just tell me your thought on this. Right, so I'll take Puma. So what is your guess? Puma, Dhanavardhan. Yes. Hello.
Big O N.
Big O N. What is the reason?
Number of iteration of the answer goes depending on the input size of the array, string array.
Okay. Okay. Very, very good. Right. So I said like, if your answer is correct, you're good. And if your answer is wrong, you're very, very good. Right. So yeah, but it is reasonable. Your explanation is very reasonable, Puma, right? Because he says it is big O N, right? It is big O N. Why is that? Because this for loop iterates n times. At every time, so we are appending one character at a time. character. So we are appending one character at a time. So the loop goes n times. Right. So whatever the value that we input here, it iterates n time. And then Arfath is having a different answer. So big O log n. So why is that? So what is your explanation, Arfath? So why you say it is big O log n? I mean, so if your explanation is wrong, that's fine, right? You better be wrong here than the exam or somewhere out there in the industry. We input n, then iterating n time with the string also update. Yes, very good point. Very, very good point. We input n. Yeah, that's true. And then iterating n times. Yeah, that's fine. N times. And then the array is updating. Right? Good point. Good point. But again, Arfath, so the answer is not correct. Your point is very valuable, but the answer is not correct. So it is not. Sorry. So we have two answers now. Big O n, and then big O log n. Right. So this is not correct. This is not correct. So why this is not correct? Why this is not correct? So any other answers? So now we have many other values like big O 1, and then log n is there, n is there, then big O n squared. Oh no, so we have n log n, big O n squared, and so on. So we have. So any other guesses? Okay, Johan. Johan says it is big O n squared. So why it is big? Why it is n squared, Johan?
Because sir, that when we add a new character to the string, the new string object will get created, right? So the internally another loop will run to copy the old string to the new string. Therefore, there is another loop. So loop inside the another loop mean should be n square. Exactly.
Very good. I mean, it is. You're good. Huh? You're good. It's the answer is correct. So big O n squared. Yeah. So this is correct. So this is correct because of the exact reason that he explained. Actually, in this case, even it is just one array internally. So we have an array. So it's the mysterious invisible array is there. So why is that? Because this is a string. So that's the point. This is a string. So string is an array. Array is immutable. We cannot change array. So if we create an array, right? If we create an array, we cannot change the size. The size is n. It is fixed, immutable, right? So if we create an empty string, so this is fixed. We cannot add any more values, fixed. So when we create, when we append, right? So with this operation, internally string handles this in a loop. What it does is it creates new array, right? Like this is empty array. It creates item with one array, and then it copies the value of previous, but it is empty in the previous case. It is empty. So then A is added. Right? A is added. Right. So then in the next iteration, it creates new array. With so now the size is 0, size is 1, and then size is the previous size plus 1. So size is 2. Size of the array. And then it copies the values of the previous array, A, and then new A is added, right? So in the next case, it will create a new array with size 1 plus. So it will copy the values of the previous array. Okay, and then new A is added, right? So likewise, so this iterates n time, but internally another array is taken place. So this inner array, it iterates, for example, in this case, one time, just to copy this value, and then this adding new, the appending. So this is constant. So always appending a value, assigning a value, it is always constant, right? It is always constant. But this copying part, it takes time. To do that, it iterates, in this case, one time, this 2. So likewise, when the array goes bigger and bigger, right? So the last time, it iterates n minus 1, right? The size is n. Suppose the size is n. So we have to copy n minus 1 items. And then finally we add A, the last. So this is n minus 1, right? It is similar to, the inner array is similar to, this one. මේ වගේ එකක් නේ inner array එකේ තියෙන්නේ. With the inner array, so it is something like so that's why it is n squared, right? N squared. So remember, when you are appending items to a string, right? It is more complicated than you think, right? So it is n squared. Right. So then this would be very, very easy, right? So another application, right? This function, so we have 3 arrays. So we have 3 arrays. Right, so we have 3 for loops, right? Yeah, it is obvious. It is n cube. If each of this original set has size n, then the worst case running time would be n squared. Right? If this condition is true, right? So if we have 3 arrays, we have 3 arrays. So we check whether like similar size, almost similar size, right? So we check whether the value here is equal to this. 3 values are equal. If these 3 values are equal, we return, we stop. Return. So see the return statement. So return false statement is there. If these are equal, A equal B and B equals C, we return false. If this condition occurs, so it could occur at any time. It could be occur when we are checking the first one. මේ පළවෙනි එකේ A කියන එක මෙහෙම තියාගෙන මේ දෙවෙනි එකේ ඔක්කොම වැලියු එක්ක යනවා. දෙවෙනි එකේ A කියන එක මේක තියාගෙන තුන්වෙනි එකේ ඔක්කොම වැලියු ටික චෙක් කරනවා. That's how it goes, huh? Then the value of the A is this one, the value of the second one would be, we go to the second one. And again, we check all the values of C. All the values of C. Right? So then the A is the same, B goes to the next one. And again, we check all the values of C. And so likewise, B goes up to this one. And then each time we check the C. So every time it n times, right? This one n times. This goes n times and this goes n times. And then after all these, so A goes to the next one. A goes to next one, and then it checks with all the B, and then this one. So that's why it is n cube. N is multiplied in 3 times, right? So however, this program could stop in just one step, right? Suppose, so we are A is this one, and then B is this one, and C is this one, right? If we check the values, if they are these are equal, so then the program could stop. The false කියලා මෙතන return වෙන්න පුළුවන්. Right. So if it happened, right? So how many times it iterates? Just one time, just one time. Then why we call it big O n cube? We can make a program එක run stop වෙන්න පුළුවන් එකපාරට. ඒ කියන්නේ පළවෙනි මේ iteration එකේම stop වෙන්න. මේක sign කරලා මේකට sign කරලා මේ ඔන්න මෙහෙම කරපු ගාම මේක stop වෙලා මේක return false වෙන්න. Yeah, the reason is we consider the worst case. So here, worst case running time would be n cube. So the worst case would be this condition is not true. මේ condition එක true නේ නැත්තම් දිගටම යනකල් මේ loops සම්පූර්ණයෙන්ම run වෙනවා. That's the worst case. That's the worst case running time. So then it will return, finally it will return true. We don't find similar values in these arrays. So that's the idea. So in big O value, so we always consider the worst case running time. Okay, so mainly that's all in this complexity analysis slides, right? So and then, so I have uploaded the next set of slides, right? Lecture 5 slide set. I mean, the most of the things that we discussed are here, right? So I have given some examples for each not for all, but for some of the. So I have given some examples. Some of these things have already discussed, right? Okay. So any questions up to now? So I'm going to go through the examples here in this set of slides. It won't take much time. So I'll take another maybe 30 or 40 minutes. So we can discuss some examples. So I will explain some special cases of big O notation. Right? So big O notation is used to classify algorithms. Right? So as I told you, right? It reflects their running time or space requirement. So I'm talking here is running time, right? So however, the space requirements, we consider it as the same, right? But in our examples, we are not taking it seriously, but space requirements can be considered in a similar manner, right? So here in these examples, we are just considering running time, okay? Grow as the input size grows, right? So in big O notation reflects the running time when the input size grows. Input size එක වැඩි වෙන්න time එක කොහොමද වෙනස් වෙන්නේ? Right, so that's what big O notation shows. So it reflects the order of the function. Which order function? One order ke function එක constant, linear, quadratic, or what is the order of the function? මොන වගේ function එකද? වර්ග පදයක්ද? නැත්නම් මේ තුනේ බලය එකක්ද? නැත්නම් බලයක් නැති නිකන් එක එකක්ද? So the order of the function, right? So if you have a constant, it is n0. n0 කියන්නේ එකයිනේ. Right? So then n1 means 1. Sorry, n squared, right? n3 to the power n, likewise. So this order is there. Order එක usually provides an upper bound of the growth rate of the function. Upper bound. No? So the constant. So one example is, I told you, right? So we have an array. So if we just access one element using the index, the algorithm will always take same amount of time to be executed, right? The array size is different. This would take always the same constant time. So constant time. We talked about this one. Log n or logarithmic time complexity. One example is binary search. I gave you binary search. Right? So we talked about binary search, right? In binary search, so binary search can be used for ordered array. Ordered array. We find the middle value, middle index. What is the middle index? And then we compare our value with this one. So based on that, we just consider one part, the left part or the right. Suppose we consider this part, and then we find the middle value. Actually, it is like we jump to the middle and then we jump into the middle of the circle. And based on the comparison, we jump to the middle of one of these. So likewise, we are jumping into the middle. Right? දෙකෙන් දෙකට බෙද බෙද යන්නේ. දෙකෙන් දෙකට බෙද. පළවෙනි එක දැන් ප්‍රශ්නේ දෙකට බෙදුවා ඊළඟ ප්‍රශ්නේ ආපහු දෙකට බෙදුවා. ඒතර මෙන්න මේ යන විදිය තියෙනවානේ. right. දැන් ප්‍රශ්නේ මෙන්න මෙහෙම පැන. right. ඊට පස්සේ මෙහෙම ගියා. ඊට පස්සේ මෙහෙම ගියා. So the jump is always half. Right. මේ මෙතනින් පැන්නා වගේ භාගයක් තමයි ඊළඟ සැරේ පන්නේ. So that is one characteristic of log n types. Right. Sorry. Right. So if you take this example here, right? Suppose I have array of n, 8, right? Array of size 8, array here, right? So then, so how many iterations? How many steps? How many steps that we have to follow in binary search? So be aware. So this is an ordered array, right? So no problem. So we can use binary search, right? So first we try to find the middle, right? So that's the first iteration. We compare and then we find which area, which part to be considered. Right. So this is iteration 1. And then next iteration, so we find the middle and then we consider. So then the third iteration, we divide that into just one value, right? One value array. Right? If size is 8, we can go to one element array in 3 steps. See, 3 steps. If we can go to one element array, definitely we can find the value. The search is finished in 3 steps. Actually, 3 and then another step, right? Another step, 3.5 steps or something, right? So generally 3 iterations, we can reach to the value that we are searching for. Maximum 3 iterations. If the size is 8, maximum 3 iterations, we can reach to the value. So the total time would be 3 times for the iteration. So like for one iteration, what is the time? And so there are some other steps, the time. So these are these are constant. C1 and C2 are constant. So the time would be equal to 3. So if the size is n, right? So size is n. Sorry, size is 8. The time it takes would be 3. So actually this is the log 8, 2 to the power, if in like the base is 2, this is 8. So 3 is log 2, 8. That means this is dekhe pade log. Okay. So you can check this for the bigger arrays, right? So take an array of dekhe pade එකක් ගන්න. ඒක ලේසි එක. මේවා කරගන්න. මොකද දෙකටනේ බෙදන්නේ මේක. You always divide that into 2, right? So in such cases, it is so if you take like 64 size 64 array, right? Check how many maximum, how many iterations it will take to reach to single value, single array, single element array. It is roughly log n. Size එක 8 නම් ඒකේ log value එක වාර ගන්නක් යනවා මේක reach වෙන්න. කියන්නේ කවුරු හරි අහුවොත් එහෙම දැන් array එකේ ordered array එකක් තියෙනවා. array එකේ 64ක් තියෙනවා කියලා හිතන්න. අර මොකක් හරි එහෙම වාර ගණන් දුන්නාම ඊට පස්සේ ඔය කටින් ඇහුවොත් එහෙම වාර කීයකින් පුළුවන්ද මේකේ හොයන්න මේ මොකක් හරි අපි හොයන value එක search කරන්න පුළුවන් කියලා ඇහුවොත් එහෙම ඒකේ log දෙකේ පාදයේ log අගය දුන්නොත් ඒක තමයි value එක roughly. So that means using 3 steps, we can reach to the value, whatever the value we are searching, if it is available. If it is not available, again, we can find that it is not available using 3 steps, maximum 3 steps. So that's the idea. All right. Okay. So that's why binary search is logarithmic. Right. So then just give me one example. Oh, no. So let's go with that example later, right? Later. So I'm going to give it as a quiz or something. Right. So then linear time complexity. Linear time complexity. It is very simple. Linear search is linear time complexity. Is having linear time complexity. So the reason is in linear search, if array is not something like this, not an ordered one, so then we have to go through the array and we have to find the value. Linear search. So in this case, actually we are printing all the values of array. So we are printing all the values. we display array items, all the values of the array. Again, it is linear. Right? If you want to print all the values in the array, so you have to go through the array using a loop. Goes from 0 to n. N times it is iterating, so it is linear time. In linear search again, so you have to search, right? If our value is equal to the value, the current value, so then in a linear search again, if we are searching for a value, suppose if we found our value at the 0th index. Suppose we are searching for 35. Suppose 35 is in the 0th index. So then with one step, so we have found the value. So however, when we give the time complexity, so we have to give the worst case. If our value is at the end, and the worst case would be the value is not in the value that we are searching is not in the array. That would be the worst case. So then in that case, we have to iterate. So we have to iterate through the whole array. So we have to go through the whole array. So that's why it is big O n. Linear search. All right, so here I have given, so it's a similar array. Actually, it's the same array, the previous array. And if we search linear fashion, linear manner, right? So then 8 iterations. Size is 8 and 8 iterations. So that's why it is n, big O n. We have to search each one. Right, okay. So here, right. Forget about this loop in this program. Forget about the first loop. Just consider the second loop, inner loop. Actually, that is what I was going to explain in the previous case. Suppose, so we have a loop. I zero, no, maybe n. I equal to. Yeah, so that's the work. I starts with n. Right, suppose n is 128. Suppose n is 128. So then n goes up to 0. Zero dakwa yanama. Sorry, I goes up to 0. Right. So I is from here to up to 0. I divided by 2. I is divided by 2. Then the first iteration would be, so I is 128. And then the next iteration, I would be 64. The next iteration, I would be 32. In the next iteration, I would be 60. Next iteration, I would be 8. Next iteration, I would be 4. There I would be 2. And then finally, I would be 1. So how many times? 1, 2, 3, 4, 5, 6, 7, 8. 8 times. So no, yeah, yes. So this loop would iterate maximum, yeah, so 8 times, okay? 8 times. Right? So this is a loop, right? So if it is a loop, just loop, it doesn't say it, the time complexity is n. In this case, actually, so we have to check how the value of I, or value the increment or decrement variable in the for loop is changing. So in this case, it is divided by 2. Divided by 2. So in this case, actually, this is not big O, sorry, big O n. It is not big O n. It is actually big O log n in this case. It is divided by 2. So basically, it is like log n, approximately log n. So if it is 128, so it is 2 to the power 28. So the value would be just a 708, right? 708 steps. Actually, in that case, 7, like it is similar to approximately log n value. Loop. So if it is a loop, so don't just consider that it is just. So if it is a loop, if it is just one loop, it is big O n. Right? Don't consider that. Actually, you have to check how the value is changing. The value is changing. Suppose if the value is changing like so. For suppose int I is 1 and then I is up to n and I multiply by 2. Again, this is the same. In this case, it would be big O log n. It is actually the opposite of the previous one. It is having log n time complexity. Right. So in this, in this example, this loop goes n times. it is iterating n times. So it is having n times, and then inner loop goes log n. So that's why it is n log n. Right, in quadratic case, n squared. So this loop goes n times, and then the inner loop goes again n times. So this is n, this is n, that's why it is n squared. But in this case, this is n log n. So that's why this program would be n log n. So that is how n log n would be occurred. So in merge sort, so we are going to learn that in the next semester. So it has something like this. It's having loop goes like this. Then exponential time complexity. So one example is Tower of Hanoi, right? So in this algorithm, so this problem, so what we have to do is, so there are 3 disks like this, right? So there are 3 bars, right? A, B, C, and then we have 3 disks. The largest disk is on the bottom, and the those are in an order, right? Like in the first step. So they are like that. So what we have to do is we should move this disk into the bar C in the same order. So finally it should be like this. So in this case, our input size would be the number of disks that we have, right? So then, so usually if it is 3, right? Size take a 3 now. How many steps that we have to follow, right? If the size is 3, how many steps that we have to follow? So first we have to move the red one to C, and then white one to B, and then red one to B, then green disk to C, and then red to A, and then white to C, and then red to C. So the number of so the number is n. So 1, 2, 3, 4, 5, 6, 7. So approximately, so the n is 3, right? So number of iterations, so number of steps would be here 7, right? So it is close to 2 to the power 3, right? So 2 to the power n. So that's why it is called 2 to the power n. 2 to the power n, exponential. So Tower of Hanoi. So most of the recursive functions can be considered as exponential. Right. Size එක වැඩි වෙන්න ඒක exponential විදිහට growth වෙනවා. So it is like so assignments එහෙම නොකරන්න assignments දැන් subjects ගොඩක assignment එකතු වෙලා අර වැඩි වෙන්නේ අන්තිමට the workload of at the end of the semester is similar, right? It is growing exponentially if you do not work in the beginning of the semester. From the beginning of the semester, if you don't work properly, so then the workload would be grown exponential like this. Huh? Right, so this is the program, right? It uses right recursion. It uses recursion. So in recursion, we talk about this in detail, huh? Right? So this is exponential. Right. So then we talked about this, right? Like the previous one, that like appending to a string. So it is n square, right? So this is searching, right? Linear search. It is, we go n, and this is this goes n, and this goes log n. So it is n log n. This is 3 for loops. Don't just say it is just n cube. First check how these values are changing. Right? It is n cube. Right? So likewise, so we can identify different time complexities in different algorithms, right? So so I have given few examples, right? But from now on, when we talk about new algorithms, so we are going to talk about its time complexity, right? So yeah, so that's the official end of this the time complexity analysis of algorithms, right? But that's not the end. So we are going to use this again and again in this semester and next semester. So from now on, we are going to compare algorithms using the time complexity. Okay. Right. So any questions? Any questions? Right, so the Dhanushika. So is it clear? Is it clear? I mean, it doesn't have to be 100% clear, but so did you get the idea? What we are doing here? Dhanushika, 1970. Dhanushika, are you there? Dhanushika, are you there?
I'm here, sir.
Okay, so is it clear? Is it clear? Like time complexity analysis, did you get the idea? Or do you have questions? Any questions? Okay, so at least if you got little ideas, very, very basic idea of this, so then so we can progress. Like you can check the notes from the beginning, and then so I'm going to give you some exercises on this, right? So I'm going to give you some exercises. Taruka Dilrukshi. Do you have questions? Any questions?
No, sir.
So is it clear?
Yes, sir.
Okay. Right. Okay, so that's all for today. So next week, so we are going to have the lecture. It's 29th, so we are going to have the lecture as usual. And then we are going to talk the next section. So this, yeah. So we are going to talk about stacks and queues. Stacks and queues next week. Right. Okay. So that's all. And anytime if you have questions, you can contact me. No problem. And then remember the first assignment, the second assignment would be uploaded, and then there will be an examination, right? Mid-semester examination in few weeks. Get ready for that, and then remember attendance, right? From this week on, so I'm checking, I'm monitoring the attendance. So if any difficulties of attending lectures, just let me know. Let me know in advance if you are having, if you have an appointment with the doctors, no problem. So just let me know, right? So other than that, like so I have some power interruptions, and also those are not general excuses, right? හැමදාම ගෙදර ලයිට් යන විදියක් නැහැ බදාදා උදේ 8ට, right? So that's the thing. Right. Okay. So thank you, and have a nice week. See you on next Wednesday.